All right. Well, hey everyone. Welcome back to our series on linear algebra. So today will be a short video. We're just going to do a little bit of application. This is really cool. This is network analysis. Network analysis. Okay, well, I'll tell you what we mean by a network, and then you'll see some cool applications for it. So let me just dive right. By the way, this is section 2.4 in the text, and I highly recommend you read the entire section. It is just a sequence of really, really cool applications, and we don't really have time or, nor is it the main focus for our class to cover all of them, but each one of them is really awesome in its own right. We just picked the best one for this one. So, my opinion, this is the best one. Network analysis. So, okay, what do we mean by a network? So, a network is a finite number of nodes or just points, okay? Sometimes they're called junctions. And then those things will be connected by a set of directed edges called branches or arcs. Arcs because, they may have to turn a little bit. But, okay, so and I've drawn a little example, right? You've got nodes A, B, and C, and branches all connecting them. A is connected to B, connected to C. Any node can have branches coming in and going out without pointing directly to another node. That would be like looking at some small portion of a larger network or something like that. Okay. Okay, but more than that, what do we do with it? We label each branch with a flow. So a flow is just a way, it's almost like a way of assigning a weight to each branch. That's the most general way I can say it, because after that, it starts to become context specific. So maybe, this first branch has a weight of 12, and then between A and C, the branch taking A to C, is some flow called F2, and we don't know what it is or something like that. Okay, so now, so this is the setup for a network. And then we have the most important rule that applies to every node in the network. And it's the law of conservation of flow, or the conservation of flow. It's just the rule that the network has to obey. And it says that at each node, if you add up if you take the sum of all the flows coming in, that must equal the sum of all the flows going out, right? We're not allowed to have any buildup at any nodes. So whatever's coming in has to go out the other side. So for example, if we focus on the point B in our little diagram, notice B has a flow of 4 and F1 coming in, but F3 and 7 are going out. So we have this equation imposed by the law of conservation of flow. Okay, great. So why would you look at something like this? Like, who cares? Okay, let me tell you about some possible contexts for network analysis. Okay, first of all, civil engineering is a huge one. If flow is like traffic, like literal traffic flow, you could break your city down into a bunch of one-way streets, say, and then just ask about the amount of traffic flowing along any given one-way street, and you want to make sure that that system is balanced, right? So that there's no buildup at any one stoplight or intersection or whatever. Social media, bunch of popular YouTubers or whatever have traffic between their channels, and you can model that using a network where each node, each node I guess would be a YouTuber. Oh, but okay, I said social media, and then I said YouTube. You know what I mean? A bunch of anything that involves connections between people and then a flow between across those connections. So for example, a communication network as well. Economics, tons of applications in economics. You just track the flow of money between, so for example, if I have some employees, I pay them. Oh, that's not good. I pay the employees, and then the employees put the money into the local market, who then turns profits, but then pays their employees and so on. You can track the amount of the flow of money in an economic system. Same thing for population. So if you wanted to model the number of deer in some different sections of the United States or something like that, you can watch population. You can watch how the different populations change over time, something like that. Epidemiology, modeling sicknesses and diseases. So this is a really common application. But if you track how a disease spreads through different communities, you have to keep track of, for example, how many people are passing back and forth through the different communities and so on. Electrical networks, literal flow of current between different power consumers. I don't know, I'm not an electrician. Dating, you can use network analysis to model the dating pool. Although just make sure you don't hurt anyone's feelings when you write down your model, okay? Your network, not that kind of model. Okay, swarm behavior. So this is actually something that I did for my master's thesis. If you imagine a rose bush and a bunch of bees swarming around the rose bush, the bees will want to stay away from each other, and so that will put some influence on the different flows between the different nodes, which would be the flowers on the rose bush or whatever. Zombie apocalypse. There's a famous example of just network analysis. I don't know the name of that problem, but essentially you just track the flow of, well, zombies. But yeah, just really anything where you can imagine nodes, lines connecting, branches connecting those nodes, and then some flows across those branches. Really, the possibilities are endless. This is a highly, highly applicable process. Okay, so anyway, by the way, this is not an exhaustive list. There's this is a really very, very common type of analysis. Anyway, okay, so that's enough of that. Let's do an example. So this is example 2.30 in the book. Okay, and I've just copied it down here. So we're going to work through this example. Notice we're handed just a picture and no instructions. The idea here is find a possible solution for F1 through F4 in terms of flows, whatever. I guess there's this is the context of this problem is that all the flows represent like the flow of water, and all these branches are like pipes or something like that, right? And so again, you don't want anything to be blocked up, so we need the conservation of flow to apply at every single node. So let's go and just analyze each of the nodes, right? That's always the first step. At node A, notice there's 5 and 10 coming in. That's 15. That has to equal to the flow out, which is F1 plus F4. So F1 plus F4 is 15. At node B, coming in is F1, and going out is 10 plus F2. Okay. At node C, coming in is F2 plus F3. And plus 5. And going out is just 30. And at node D, coming in looks like 20 plus F4. And going out is F3. Great. Now, if that looks like a system of equations, you're absolutely right. I'm going to rearrange them and write this as a system of equations that looks like something that we would recognize. So the first equation might be F1 plus, let me leave some space, plus F4 equals 15. The second one might be F1 minus f2 equals 10. Right, subtract f2 from both sides. The third one, f2 plus f3 equals 25. After subtracting 5 from both sides, of course. And the last one, if we subtract f4 from both sides, you'll get f3 minus f4 equals 20. Okay. So this is a system of equations, and we know what to do, right? We solve the system. So Gauss-Jordan elimination, I guess. Let's write down an augmented matrix. The augmented matrix is a bunch of ones. That's going to make the row reduction easy. Looks like 1, 0, 0, 1, 15, 1 minus 1, 0, 0, 10, 0, 1, 1, 25, 0, 25, and 0, 0, 1 minus 1, 20. Row reduce. Okay. I notice in this matrix ones that look like good candidates for leading ones in reduced row echelon form. So my first step is going to be to interchange row 2 and row 3. And then row 3 with row 4. That's just to put row 2 at the bottom and shift the other two up by 1. So what that will do is the following. 1, 0, 0, 1, 15, 0, 1, 1, 0, 25, 0, 0, 1, minus 1, 20. And the last row will be what was the second row. 1, minus 1, 0, 0, 10. Next, I want to turn those ones into zeros. So that's I mean, I guess technically that's pivoting around the two leading ones in those two columns. And while we're at it, let's also turn this one into a 0. That should do it. That should put this in reduced row echelon form, actually. So let's just do that. So what are those moves? We've got row 4 minus row 1, row 4 plus row 2, and row 2 plus row 3. Okay, and what that does, okay, the first row doesn't change. 1, 0, 0, 1, 15. Then the second row will be 0, 1. Now, sorry, if I add row 3 to row 2, that's not going to work. That's going to put a 2 where I want a 0. I have to subtract row 3 from row 2. So row 2 minus row 3. So 0, 1, 0, 1, 0, positive 1, and then 25 minus 20 is just 5. The third row doesn't change. 0, 0, 1, minus 1, 20. And now row 4. So row 4 is going to have a 0 because we subtracted row 1 from it. And then another 0 because we added row 2 to it. And then a 1 because we added row 2 to it. And then a minus 1 because we added row 1, or because we subtracted row 1 from it. And this 10 is we have to subtract 15, but then add 25. 10 plus 25 minus 15 is 20. So that you've seen it once, if you have two copies of the same row, subtract the second one from the first one, and then we'll be in reduced row echelon form. But notice that last row is just redundant. So row 4 minus row 3 is our final step. And I am not going to rewrite the whole thing. I'm just going to copy paste. Great. Okay, so let's read off our final. We'll rewrite this as the corresponding equivalent linear system. So F1 plus F4 is 15. F2 plus F4 is 5. And F3 minus F4 is 20. And of course, F4 is free. Let's parameterize our final. We'll parameterize our final solution. So F1, F2, F3, F4 is I'm getting 15, 5, 20, 0 plus t times minus 1, minus 1, 1, 1, where t is just F4. Okay, and I'm actually going to write this in parametric form. So let's just write this as 15 minus t, negative 5 minus t, 20 plus t, and t. Reason I might want to do that is because we have to this problem has context. So if we were just trying to find the intersection of a bunch of planes or something like that, we're done. However, this problem has context. It's like fluid flow. So we want to know, for example, what values of t are possible. Well, you could have, one thing that we want is to avoid having negative flow, right? If the cars on the street are going backwards, or if the water in your pipes is flowing backwards, that's really bad. So we're going to ask that that Fi is greater than or equal to 0 for all i's. Right, so F1, F2, F3, F4, all greater than 0. Now, that means that all the entries in this column vector of solutions have to be positive numbers. For any positive numbers for t, that'll be true of the bottom two. However, if t is a negative number, that bottom entry will be not allowed. Will be a negative number, which we're not allowing. So we definitely know that, so because of F4, t has to be greater than or equal to 0. Now, if we try a giant positive number, if we tried t equals 50, well, the first two entries are going to be negative because we're subtracting t. If we pick t equals 15, The first entry, f1, is equal to 0, and any number smaller than 15 will make f1 positive. However, for f2, even if you picked like t equals 10, f2 will still be negative. So we have to go down to at most 5. So because of f2, t has to be at most 5. Okay, so we don't have a huge range of values. T could be any real number, right? Between 0 and 5. So I'll just put, so thus, like this. T belongs to the interval 0, 5. Closed interval, so we're allowing the endpoints. We're not quite done. We have to ask, like, okay, knowing t is nice, knowing possible values for t is nice. But notice that all of these functions, of course, they're linear because you know how it is, which means they're either strictly increasing or decreasing, which means they'll attain their maximum or minimum on the endpoints of this interval 0, 5, t going from 0 to 5. So let's plug in values for t. When t equals 0, we get that f1, f2, f3, f4 is precisely that vector 15, 5, 20, 0. 15, 5, 20, 0, right? Just plug in 0 for t. And if you plug in 5 for t, so when t equals 5, f1, f2, f3, f4 is 10, 0, 25, 5. Again, just plug in 5, t equals 5 for the other vector. And now, so we have a final description. For all the possible flows in this system. We have that like 10 is less than or equal to f1, which is less than or equal to 15. 0 less than or equal to f2, less than or equal to 5. 20 is less than or equal to f3, which is less than or equal to 25. And 0 is less than or equal to f4, which is less than or equal to 5. So I'm just going to take this and return to the original diagram. And just put it off to the side here where we can barely see it. Perfect. And just verify with our intuition that this is correct. Right, so let's take a look. Say, for example, f2 needs to be between 0 and 5. Let's go to f2. And we're looking, and also let's take that combined with f3 has to be between 20 and 25. So suppose f3 is 20. Flow in matches flow out, which means f4 has to be 0. But then flow in, flow out, if f4 is 0, 15 in, f1 has to be 1. Sorry, f1 has to be 15. But flow in, flow out, if there's 15 coming in, 10 is going out from B, which means 5 has to be flowing out here. at F2. But that's exactly what, notice all of those fall right within the bounds that we laid out here. And if we check it, 5, okay, if F2 is 5, F3 is 20, we've got a 5 also coming in here. That's 30 in, and here's your 30 out. So everything checks out when we do this. As soon as you fix one of these values, fix a value for t, let's say, everything snaps into place. Our hands are completely tied. So great. Okay, that's it. That's it for this video. Nice short video. Something interesting. So next time we're going to be starting chapter 3, which is all about working with matrices. So I hope you'll enjoy that one, but I will see you in the next video.